Have you ever thought about how your phone gets charged? I mean, you might be like, duh, we use electricity. Yes, but how? How does the phone hold electricity? And you might be like, duh, we use a battery. But what is a battery? Like how does a little piece hold electricity? And what if I told you that it is a chemical reaction? It involves all the chemistry and all the chemicals that we've been talking about. So today, that is what we're going to be talking about. We're going to talk about electrochemistry. What is electrochemistry? If you think about this word, it has electro in it and chemistry. And it is a way we generate electricity by using chemicals. It's the easiest way to think about it. And another way to think about it is like the electro comes from electrons, right? And guess what electricity is? It's the movement of electrons. When electrons move, they create electricity, right? So we're going to use chemicals to move around electrons. That is what electrochemistry is. And that is what today's topic is about. Now, when it comes to electrochemistry, right, we are talking about element A, right? They say element A, right, loses electrons, and we talked about you've seen this before, right? Element A can lose electrons, and what do we become when we lose electrons? We become positively charged. So A can become A plus plus 1 electron. Let's say it loses 1 electron, and guess what? B, that's already positively charged, can gain 1 electron to become B, right? So positively charged because it needed an electron. Now we gain that electron, right? So electrochemistry involves the movement of electrons, and the movement of electrons is going to be like, okay, we are losing electrons or gaining electrons. So I wanted to write this down before I dive into this next part, which is when it comes to electrochemistry, we have things that are losing electrons and things that are gaining electrons. So we have terms that I don't want you to be confused on. So let's say A here, right? Like A that I just drew up here, A is losing electrons, right? When A loses electrons, right, it undergoes something called oxidation, right? Oxidation is the act of losing electrons. And guess what? When it undergoes oxidation, you still with me? It becomes oxidized, right? A, the thing that loses electrons, undergoes oxidation, and it becomes an oxidized atom. And look at what happens to B. B undergoes reduction, meaning it gains electrons. So oxidation is losing electrons, reduction is gaining electrons, and guess what it becomes? It becomes reduced, right? So far so good, right? We undergo oxidation, we become oxidized. We undergo reduction, we become reduced. And this is where it gets like a bit confusing. It's not very confusing, but the thing that undergoes reduction and becomes oxidized is a reducing agent. We call it a reducing agent. Why? Because as it undergoes oxidation, meaning as it loses electrons, it gives the electrons to this other agent. So it's a reducing agent because it helps reduce. It helped reduce B. So this is where people get confused, right? They think that the thing that undergoes oxidation is an oxidizing agent, but no. The oxidizing agent undergoes reduction, right? Meaning the thing that loses electrons and become reduced helps oxidize A. Does that make sense? I think that makes sense, right? We have an oxidizing agent and reducing agent. reducing agent undergoes oxidation, becomes oxidized. And oxidation means losing electrons, right? So these are very important terms when it comes to electrochemistry. So an electrochemical process, and again, is oxidation reduction reaction, right? Oxidation reduction reaction, because now we know what oxidation and reduction is. These are oxidation reduction reaction. We sometimes call them redox reaction, right? Redox reaction, which is reduction and oxidation reaction, right? So they are electrochemical reactions. Why? Because the energy released by that reaction, right, can be converted into electricity, right? Or the reverse is true. You can use electrical energy to cause non-spontaneous reaction to occur, right? So electrochemistry can go both ways. That's actually a good point, right? Electrochemistry can go both ways. We can use electricity to perform chemical reactions, or you can use chemical reactions to produce electricity, right? So this is an example. Look, 2 mg plus O2 is equal to 2 mgO, right? I want you to pay attention here. There's something we call an oxidation number or a charge, right? Look at this. Magnesium has a charge of 0 here because it's not bound to anything. Oxygen has a charge of 0 here, but magnesium bound to O, right? If you remember our ionic compound, magnesium bound to O has a charge of +2. Oxygen is O2. So we went from here, from oxygen went from 0 to 2 minus, magnesium went from 0 to 2 plus. So which one lost electrons? Magnesium lost electrons, right? Magnesium lost electrons and underwent oxidation, and then oxygen gained electrons because it became 2 negative. Remember, 2 negative means we gained electrons, so oxygen gains 2 electrons. It undergoes reduction. So if I give you, this is a oxidation reduction reaction, and then what we're going to do is we're going to go to write down what we call half reactions, right? Half reactions is kind of like here, right? It's like I gave you, so the whole reaction will be A plus B plus becomes A plus B, right? This is a whole reaction, and then you break down the whole reaction into half reactions, right? So same here, the half reaction is magnesium plus magnesium 2 plus equals 2 electrons, right? And then the other half reaction is O2 plus, it becomes O2 minus. So we adding electrons here to balance, right? So if you were to do a half reaction, you wouldn't add electrons yet. So this is how you do. If I ask you to do a half reaction, you'll be like, okay, magnesium became magnesium 2 plus. So magnesium became magnesium 2 plus, right? And then plus 2 electrons, because 2 plus means we've lost 2 electrons. And then the other half reaction is going to be like, O2 became O2 minus, right? And then you're going to be like, oh, okay, yeah, but in order to do that, that means we gain electrons. So it's oxygen that gains 2 electrons. But then you look at the stoichiometry here, you see that the stoichiometry, in the balancing at least, right? In the balancing, you have 2 magnesium, meaning that we multiply our electron by 2, right? And then here you have O2 plus 2 electrons equals to O2, but it's not balanced, so it's 2 here, which means it's 4 electrons, right? So this is how we do half reactions, right? But again, let's go back here and talk about what I say was oxidation number, right? How do you get these numbers at the top, the oxidation numbers? Well, the way we get the oxidation numbers is through a few rules, right? So if you have a free element by itself, like sodium, barium, potassium, or even, like H2O, O2, right? These will still have oxidation number of 0, right? The oxidation number of 0 for free elements, even if they are diatomics, right? Now, and then in monoatomic ion, right? The oxidation number will be the charge. If you remember, we know the charges. We should know the charges of the ion, right? And then oxidation number in oxygen is usually -2 most of the time, right? Sometimes in like H2O2, we'll violate that rule and then have oxidation number be -1, but in most of the time is +1, right? Not +1, but -2. All right. Hydrogen is most of the time +1, right? Sometimes it's when it's bonded to metals, something like if you have NaH, right? Na will have +1, H will have -1, right? But in most of the time, like HCl, right, this will be -1, this will be +1, right? So this is how you get the numbers. Group 1A elements are +1, so these are lithium, sodium, potassium, to go all the way down to the periodic table. Group 1 is +1, group 2 is +2. Fluorine is always -1, so fluorine, chlorine is always -1, and all that stuff. And then the sum of oxidation numbers, right? If you don't know which one, the sum of these numbers should be equal to the charge of the molecule. What do I mean by that? If you have HCl here with no charge, it means that the charge is 0, right? So if chlorine is -1 and you know that hydrogen has to be +1 for it to be 0, right? That's why hydrogen here has to be -1, because sodium is +1. Hydrogen has to be -1 for this to be 0, right? Now, if you have like something like CO3 minus, right? Same thing, the sum H2. So this is CO3 2 minus actually, right? But the sum of these has to be 0. So if I ask you like, what's the formal charge of carbon here, right? You're gonna be like, oh, okay, I know the formal charge of oxygen is -2, and guess what? I have how many oxygen is 3 of them, right? So 3 times -2, right? And then carbon is just 1, so let's say X is X, right? It's X plus 3 times -2 is equal to, this will be equal to the charge of this whole group, which is -2, right? So then it's gonna be like X plus, not plus, because 3 times -2 is -6, so X minus 6 is equal to -2, right? And look at this, X is equal to -2 plus 4, right? Plus 6, plus 6, which is equal to +4. So the formal charge for carbon here, for this to get, so for CO3 2 minus, to get 2 minus, oxygen has to be -2, carbon has to be +4 for the whole thing to get 2 minus, right? So we really do care about oxidation numbers, and we'll get to practice in a minute, but we care about them because we need to know how to balance redox reactions. This is one of the most important things when it comes to electrochemistry. I would say that this might be, I was gonna say this is the hardest thing, but it's not hard. It's not hard at all. So just bear with me. We are going to go through these steps, right? Because the way we balance these reactions is kind of a bit different compared to how we balance other reactions, and I'll show you, right? So I will give you something like, hey, we're going to do if we oxidize Fe to 3+ by chromate in acidic solution, what's going to be, like, balance it, right? Balance it. So first, to balance it, we're going to write down a full reaction, right? And you realize, first of all, that it's not only severely underbalanced, but you'll notice that you even have atoms that you don't have on the other side, and that's okay, right? You have oxygen here, you don't have oxygen on the other side, right? So you're gonna be like, what is happening here? That's okay. Just first step is, after you have the balance, the unbalanced equation, right? You're going to divide it into the half reactions, right? Just like we did earlier, you're gonna be like, okay, Fe2 plus is turning into Fe3 plus. Is it gaining electrons or losing electrons? It's losing electrons. How many electrons? It's losing 1 electron, right? So Fe2 plus is going to go to Fe3 plus, and this is giving us, it's giving us oxidation, right? And then chromium, right? Chromium is going from, okay, so you gotta find like the formal charge for chromium here, right? If you do the formal charge just like we just did for carbon, you realize that chromium has to be 6 plus, and then it becomes 3 plus. And let me show you again so that you know how to do it. So CrO7 2 minus, you're gonna be like, okay, what is the number for CrO7? Well, oxygen is always -2, so -2 times 7, right? And then Cr is 2 of them, so it's like 2x, which is, 2 of these plus this much is going to be equal to what? To this charge right here, -2, right? So you're gonna be like, okay, 2x minus 14 is equal to -2, right? So 2x is equal to -2 plus 14, which is 12. X is equal to 6. So the charge for chromium is +6. Right? So this is algebra. I'm pretty sure that everybody taking this class has taken algebra. So this is how you get the formal charge, because it's very important, right? It's very important to know like the formal charges for both of them, right? Iron is already given here, no problem. All right, so this tells us that we're going from a big number, like a plus to less, so we are gained electrons. So if the number is going down like this, we gained electron. If the positive number is going up, we have lost electrons. Why? Because if you remember, the electrons are negative. All right, so the next is this, right? And this is the weird part, and I want you to stay with me here, right? We are going to balance the atoms, but we're going to ignore hydrogen and oxygen for now. We are going to take care of the oxygen imbalance here, so we're going to balance chromium, right? So if you have chromium 2 here, you're going to put 2 here, right? So now putting them together, right? We're going to have, so putting it all together, you're going to have like, so far you're like, okay, I have Fe2 plus, right? Fe2 plus becomes Fe3 plus 1 electron, right? That's 1/2 of it. The other half is Ca2O7 2 minus becomes 2Cl3 plus, right? So you see, this is what happens, but again, it's not balanced because you have oxygen on one side, you don't have oxygen on the other side. So we're going to take care of that. How do we take care of that? It depends on the conditions, right? So we will tell you, I will either tell you like it's in an acid solution or it's in a basic solution, right? It's in an acid solution or it's in a basic solution. If it is an acid solution, we are going to add water on one side and hydrogen on another to balance the atoms. Right? So I know it's weird, but that's what we gotta do, and it works out. So you're gonna look at oxygen and be like, oh, okay, I have 7 oxygens here. How do I use oxygen? Since I have acidic conditions, I'm going to balance oxygen with water on the other side. So if I have 7 oxygens, I need 7 oxygens on the other side. So I'm going to put 7 on this side so that I have 7 oxygen, 7 H2 on this side. And then you're going to be like, oh, now that I've added 7 water here, I've just added 14 hydrogens. So then I got to put 14 hydrogens on the other side to balance it. Does that make sense? If it doesn't make sense, that's okay. We're gonna look at we're gonna make sure that you understand. But again, you balance it with H2O and H plus, right? So once you have this, so now you have two half electrons. So you have these half electron and then two half reactions, right? You have these, but then you're like, okay, but the electrons are not there. The electrons are not balanced. So let's add electrons to balance the charges. Why? Because look at this, right? The charges here are what? The charges here, right, are going to be plus 3 charges, right? The charges here are plus 6 because you have 2. So if you have plus 6 charge here, right, then you come back here, you're like, no, I have like plus 14 from here, and then I have negative 2 from here, right? So the charges here are not balanced. And if the charges are not balanced here, you gotta add the charges, right? So you're gonna be like, okay, if I have these charges, how do I balance them? Oh, actually, no, never mind. We are not going to count. We are not going to multiply the charges. The charges do not multiply when you add the stoichiometry. So the charges here are plus 3. The charges here is negative 2. The charges here is plus 1. All right. So it's going to be like, okay, now I'll have to equalize the charges. How many electrons do I add on either side to make sure that we are equal, right? And then you're going to make sure that you also relate it to the other half reactions. So we have 2 half reactions. It's not just one. You have 2 half reactions, right? So you add 6 electrons here in order to balance, but then this one also has to multiply with 6 electrons. All right? So we are going to make sure that all of the electrons are going to be canceling out. But hold on, let's make sure that we're actually not confusing ourselves. I think I said something wrong here. All right, so let's dial it a bit back here. Let's delete these, right? Let's delete this and actually count the charges correctly. Let me actually move this here so that, not that, okay. Let's move this, there you go. Let's move this here. Perfect, all right. So, not that one. What happened here? Okay. This one. All right. Yeah, because I don't want to confuse myself, because if I get confused, you get confused. All right. So here we look at the charges. Be like, okay, are these charges balanced? Are these charges balanced, right? We're not looking at this one, so because we turn this into that one, right? Are these charges balanced? No, they are not, right? Because here you have chromium 3 plus, and then you have 2 of them, so it's plus 6. And then here you have 14 H plus, so you have H plus, and then you have 14 of them, so it's like 14 plus, and then so plus 14. Here he has negative 2. What's the charge here? The charge is plus 12, right? So you have plus 6 here, you have plus 12 here. How do you balance both sides? You're going to balance both sides by adding electrons on the one that has the bigger number. Why? Because electrons are negative, right? And how many electrons do you add? You add the difference, right? So here, if I add 6 electrons here, is equivalent to me saying minus 6, so that it is equal to plus 6, and we have equal charges, right? This is how we decide what electrons to add on the other side. Very, very important, right? Because after you've added those electrons, then that's going to be your currents. What do I mean by that? Since you've added 6 electrons here, since the electrons need to be balanced, we're going to multiply the top reaction by 6 as well, so that we are able to cancel the electrons. So eventually the last step is putting these together, making sure the electrons are equal so that we can cancel our electrons and then put everything together, right? And the way to verify that you've done it correctly is to use to count the charges, right? To count the charges. So this is plus 14 minus 2, that's 12, plus 6 plus so plus 12, right? That's 0, right? Wait, plus 12, that's 24, and then on the other side is 6 times 3, which is 18, right? 18 plus 2 times 3, which is 6, right? 18 plus 6, which is also what? 24. All right, so we're going to make sure that the electrons are equal on either side. And if you remember how we learned balancing in general chemistry 1, we're just counting the atoms using their coefficients. But here, when we are balancing redox reactions, we involve electrons and charges, right? So we got to make sure that the electrons are balanced, the charges are balanced, and then sometimes you will have to add H2O on one side and water to the other, right? Very, very important to remember. And again, it can confuse people, but when you get confused, just come back and look at these. Let's look at another example, right? Another example is iodide ion and permanganate ion, right? And then they're in basic solution, and they give you iodine and then MnO2, right? So what do? Step 1, the solution, right? And the solution, I mean, they not the solution, but the equation, and the equation is given in the question. So this is a manganate ion becomes MnO2, I negative becomes I2. No problem, right? So here again, as you can see, MnO2 4 minus becomes MnO2, and then I becomes I2. And if you haven't noticed already, Mn is our main atom, and then I is our other main atom, right? So you're going to step 2, you're going to measure their oxidation number, right? Their oxidation number, not the oxidation number, yeah, the oxidation charge, right? So I negative going to I2, going from -1 to 0 is what? We are losing an electron, so it's an oxidation. And then you can calculate, and you should be able to by now calculate the charge on Mn. It is +7 here. How do we get +7? You have oxygen, right? If you remember, oxygen is, right? If you remember, oxygen is going to be -2, right? So look, X plus oxygen is -2, and we have 4 of them, right? So -2 times 4, right? What is it equal to? is equal to this -1, right? So x minus 8 is equal to -1, and then x is going to be equal to -1 plus 8, which is 7. So this is how we get 7 here, and then we do the same thing. You get plus 4 here. How do we get plus 4 here? I'm just going through this one more time so that you can, practice how to do this. Is Mn, which is x, oxygen is -2, so plus 2 times -2 is equal to what? Is equal to 0 in this case, because we don't have a charge on MnO2, right? So it's like x minus 4 is equal to 0, so x is equal to 4, right? So we went from 7 to 4, that's reduction. We went from -1 to 0, that's oxidation. These are our half reactions. So that's step 2. These are half reactions. Step 3, we're going to balance each half of the reaction, but, kind of neglecting oxygen first, right? So it's like here you have I negative to I2, we put 2 in front of I, right? And then make sure that you have electrons. So 2I plus I2 is equal to 2 electrons, right? And then here they are telling you that we are doing the next part. The next part is going to be like, yeah, Mn is balanced, so we don't have to balance Mn as well. But then now we're going to be like, okay, since you have 4 oxygens here and 2 oxygens here, as we did on the other one, what we do, we put water on one side, right? You put water on one side to balance, and then you realize, okay, if I have 4 oxygen here and 2 oxygen, I need 2 oxygen on this side. That's why we added 2 water, right? Because 1 water has 1 oxygen. And then when you add 2 water, you realize that you have 4 hydrogens. So on the other side, you add 4 hydrogens, right? What's the next part? You remember the next part? The next part is now to balance the charges, right? Now that we have added these, we might have an imbalance of charges, right? So we're going to count the charges. Now, you can pause this video and see if you can figure it out, but check this out, right? We have 4 plus here, right? You have plus 4 here. And what do we have here? We have -1, right? So because MnO4 is -1, right? -1. So on this side, we have plus 3 total. And then what do we have on this side? We don't have any charge, right? We have 0, 0, right? So we don't have any charge, and then we have plus 3 on that side. And then what do we do? If you have plus 3 on this side, right? You have plus 3 on this side, right? Then you're going to figure out plus 3 on this side and 0 here. Then where do we add electrons? Do we add electrons on this side or that side? We add electrons on the part that has plus 3. Why? Because electrons are negative. So in order to add -3 here to balance, you're going to add 3 electrons here, right? So that it's going to be 3 electrons will contribute to -3, and then we're going to be 0 here, right? So it's going to be that we're going to add 3 electrons on this side, and now we have 0 here, 0 here, right? And then what is the next part? The next part is to make sure, and to go back to our half reaction. So our half reactions here is, this is the half reaction, the one half reaction, the other half reaction is this. Now check it out. We have 2 electrons on one half reaction, and then you have 3 electrons on the other half reaction. We're in trouble. We're not in trouble, but we gotta make sure that we have all the same number of electrons on all. So the easiest way to do this, you have 2 electrons here, you have 3 electrons here. The easiest way to have the same number of electrons is to multiply 3 by here and multiply 2 by here, so that we have 6 electrons on either one, right? So you're going to multiply 3 by one side, 2 by one side, so that in the end we end up with 6 electrons. And then when you have 6 electrons, we can cancel them out and get a final equation. All right, so that is balancing, right? Balancing is pretty it can be pretty tedious, but please do not get lost. Just use the steps that we just outlined, and if you get confused on one of the steps, be sure to take time with it to figure it out, and then you can ask me questions and I will walk you. If you can reach out, I will walk you through it as well. But in your question, right, this one we just did, so don't worry about that. The first one we just did, so let's skip that, and let's see if I can add another one very quickly, because I want you guys to be able to practice this, right? All right, so let's do this one instead. Yes, okay, so yeah, do these two because we just did this one. You can write it down if you want, as practice, but go ahead and balance these three as you practice. That's your first question, right? But that was balancing. Let's go to the next part, which is what we call a galvanic cell, right? So a galvanic cell is what a battery really is. And what it really is that, let me get a simple version of it, right? So if you have like a redox reaction, right, with the half cells, like this, what it means in terms of electrochemistry or battery is that we are, one of these is losing an electron, one of this is gaining an electron. So if you can separate these equations, if you can separate these, then these two electrons can move from here to here. And guess what? The movement of electrons is what electricity is. That is the definition. So if you can trap this movement of electrons, you can basically, power your lights, power your car, and all that stuff. And that's what it does, right? Your battery in your car is an electrochemical cell, right? So this is called a galvanic cell, where one half reaction happens in one container, another half reaction happens in another container, and then we connect them. We connect them by what we call a salt bridge, right? That's a salt bridge. And then in addition to that, we are going to connect to add a metal. We call these electrodes, right? So here, look, zinc, when it loses 2 electrons, becomes zinc 2 plus. So you have a zinc metal and then a zinc solution that's zinc 2 plus, right? And then guess what? These 2 electrons go through the salt bridge to go to where? To copper solution. So copper 2 plus gets those 2 electrons and becomes copper solid. That's why we have a solid copper electrode here. So copper starts to be deposited here, right? These two things again are called electrodes. And where you have oxidation, you have anode. Where you have reduction, you have cathode, right? So make sure that you're tracking it. If you remember correctly, the thing that I talked about first is you have oxidation and reduction. Oxidation is loss of electrons. Reduction is the gain of electrons, right? And then a reducing agent undergoes oxidation and then it's oxidized, right? But now we are that at oxidation, you have an anode. At reduction, you have a cathode, right? And by the way, since electrons are going from one end to another, so these electrons are going from one end to another, right? This is a positive, this is a negative, this is a positive end. So the anode is negative, cathode is positive, right? So if you can catch this movement, guess what? You just made electricity, right? So if you add a voltmeter here, it will start reading voltage, right? That's how you know that the reaction is happening. It will start reading voltage, right? So these are the half cells in a galvanic cell, or we call it a voltaic cell as well. Voltaic cell because it's producing voltage, right? So these are very important concepts here. So here I want you to write a full cell diagram of a galvanic cell that has an aluminum electrode and then a copper electrode, right? One thing that's very important is you have to tell me which one is the anode, which one is the cathode. And this is important because guess what? How do you know what undergoes reduction, what undergoes oxidation, right? Because here you have copper and copper 2+, and then aluminum and aluminum 3+. So it's like what undergoes reduction, what undergoes oxidation. Well, this comes from a table that you should have in your book that's called reduction potentials, right? So each one of these, each metal has a reduction potential, right? And this is it. This is how you know. The metal with the highest reduction potential undergoes reduction. The metal with the highest reduction potential undergoes reduction, and then the metal with the highest oxidation potential. We only read this in reduction potential. So the metal with the highest reduction potential undergoes reduction, and then the other one will undergo oxidation, right? Meaning that the metal with the highest reduction potential will gain electrons, and then the other one will lose its electrons, right? So make sure that you build something that looks like this, right? Where you give me the anode, the cathode, the half reactions, the cell. So build this in terms of these two, okay? And that's your second question. Well, after we know how to build this, then we should be able to, from that table, we should be able to measure the potential, right? We should be able to we measure the potential here using a voltmeter at the top, but we should be able to calculate the potential as well. So the standard reduction potential are going to be the voltage associated with the reduction reaction, and they are standard. When they are standard, it means that these are reduction potential that were measured when you have 1 molar of all the reactions, right, at 1 atmosphere at 25 degrees Celsius, right? This is the reduction potential, right? So each one of them will have that. But if you have that table, you should be able to measure a total. So if you have the reduction potential of half reactions, so let's say I have reduction potential of this, I have the reduction potential of this, and then we want to know the full reduction potential, right? The first thing you're gonna be like, okay, what undergoes oxidation, what undergoes reduction? You have that. And then what's the full reaction? You have that. And then if you have the numbers, right, if you have the numbers, which you should for all of these, right, you can then take the standard of the cell, right, which is the standard at the cathode minus the standard at the anode, the voltage. So the standard, so the E cell is also voltage, so don't be confused, right? Voltage, right? And E at the cathode minus E at the anode. Another way to think about it is the E of the cell is equal to E of the reduction, right, minus E of the oxidation, right? So this is how you measure the E of the cell. But again, as you can see, the very important step is knowing which one is at the reduction, which one is oxidation, because if you don't do it right, guess what's going to happen? You're going to switch them, right? So make sure that you know which one is which. Okay, very important. And this is the table. This is the table that I've been talking about. This is the table with the standard reduction potentials. So you should have it here. You should have it in your book, and from there you should be able to tell me the voltage, right, of any of these cells, right? Because again, you should be able to tell. So let's look at another example actually, right? Predict what will happen if bromine is added to solution. Ooh, this is actually pretty good, but this is different. So this is, if you remember, this is the common ion effect, but we're looking at it in terms of reduction potentials as well. But again, same thing. Here is what happens to the anode versus what happens to the cathode. You're going to set them up, right? From that table, you're going to see which one undergoes oxidation, which one undergoes reduction, right? And then you can calculate it, right? So basically this question is asking you, like, what will happen if you have these things, which one will undergo reduction, which one will undergo oxidation, all right? And that is exactly what ends up happening, all right? All right, so a galvanic cell consists of magnesium electrolyte. So you have magnesium electrode, and then you have magnesium solution, and then you have silver electrode, and then you have silver solution, and then calculate the standards. Well, number one is which one is undergoing oxidation, which one is undergoing reduction. So let's actually do this one together, right? So one is magnesium to Mg2 plus, the other one is Ag to Ag2 plus. So if we can zoom in into our table, let's find where magnesium is. So I see Ag, right? So Ag plus becomes Ag, right? Is that the one? This is so big. Okay, let me make this smaller. So I'm looking for magnesium. So that's magnesium 2 plus becomes 2E. Look at the number, negative 2.37. That's magnesium, right? The other one is, so we have magnesium, and then we have Ag to Ag plus. I was just looking at that. Okay, Ag to Ag plus becomes, ooh, okay, so this is 0.8, right? So one is 0.8, the other one is negative 2.37. So which one is bigger? 0.8, right? So that means that Ag2 plus undergoes reduction, magnesium undergoes oxidation, right? So going back here, I'm gonna be like, okay, Ag2 plus, Ag undergoes reduction, and then magnesium undergoes oxidation, right? So Ag going reduction, if you remember, what does reduction mean? Gaining electrons. What does oxidation mean? Losing electrons. And I like to write oxidation first. Magnesium, which undergoes oxidation, is going to become magnesium 2 plus 2 electrons. That's oxidation, right? And then what is reduction? It's the opposite. Ag plus, right? Plus, and I'm doing Ag plus, guys, because that's what the Ag and AgNO3 should give you the hint that Ag has a charge of +1, and then magnesium +2, right? +1 electron becomes Ag. So this is what reduction is. So these are the half cells oxidation, reduction. And then what is the full equation? In order to write the full equation, check this out. We have to multiply this second one by 2. Why? Because if you remember how to balance this, we have to multiply by 2. Luckily, this one doesn't have oxygen, so we don't have to, like, do both of them at the same time. These ones that are out here are like spectator ions. We're not going to use them, right? So it's just the metals. So if I multiply this by 2, it's going to be 2 here, 2 electrons, so that these 2 electrons can cancel out, and it's going to be magnesium plus 2 Ag to Ag plus becomes magnesium 2 plus 2 Ag. By the way, guys, notice that they really didn't ask us to do that. They didn't ask us to like write down the half reactions, but I might ask you this, so that's why like I'm doing it, because I might be like, hey, write down the half reactions of this reaction, or write down the full reactions of what's happening. So this is what's happening, but they are not asking this. What they are asking really is the standard. The standard is very easy, right? If you remember, we're going to do the standard is going to be, or the change in standard is going to be E cathode minus E anode, right? Or in the other words, E reduction minus E oxidation. So if we just looked at it, what was it again? E the reduction is 0.8, right? 0.8, and then this is potential, so it's in voltage, right? It should be in voltage. So 0.8, the other one is negative 2.37, right? So it's 0.8 minus negative 2.37 volts, right? So the voltage here should be zero point 0.08 2.45. All right, so the voltage is 2.45 volts. Right, no, it's 0.8, not 0.08. Okay, sorry, 0.8 plus 2.37. No, it's 3.17 is equal to 3.17 volts, right? So that is how you find the voltage. So question here is calculate the voltage, right? The voltage of the cell for the following reaction, right? That's your third question, but B for this is calculate delta G for reaction. What do you mean calculate delta G? Because that's what I'm about to talk about. You can calculate the energy of the reaction if you have the voltage. How do we calculate it? If you remember, this delta G means spontaneity, right? Or gives free energy. So if you're looking at spontaneity of the redox reactions, this is the equation. Very important question, very easy, right? So delta G is equal to NFE of the cell, right? And what's N? N is the number of moles of electrons. What do I mean there? It's just the number of electrons, right? Meaning that, for example, here, the number of electrons exchanged here is what? 2 electrons. That will be your N, right? Here, for example, the number of electrons exchanged, 2 electrons as well. Oh, it's pretty cool. Looking at one that has different numbers. Here you have 6 electrons, right? The ones that we canceled out. So the N for this will be 6, okay? So delta G is equal to negative N, right? So delta G is equal to negative N, which is the number of electrons. F, which is the Faraday constant. This number is a constant, it's given to you, and it's almost always 96,500, right? And then E is the voltage that you calculated, right? So if you calculate the voltage, you can calculate the delta G very easily. And if we remember correctly, right, after you calculate the delta G, you can also calculate the K, right? So if you remember, the K is, so if you remember, delta G is equal to negative RT ln of K, right? What is K? If you remember correctly, it's the equilibrium constant, right? So I don't want you to be like memorizing a lot of new equations. So again, since you already know this from thermodynamics, delta G is equal to negative NFE, right? And then this will tell us whether or not it's spontaneous, right? Spontaneity, right? And then if you remember here, delta G is also equal to negative RT ln of K, or KC or KEQ. And then if you remember this equation, we can turn it into K. If we want K, we can say K is equal to E to the negative delta G over RT, right? So this is the same equation, but if we're looking for K, we can turn it around and give us that. So that is an easy way to go from potential, cell potential, to delta G, to K EQ, or equilibrium constant, right? So I can ask you either of these and you should be able to tell me. And looking at these equations, right, we can kind of infer what happens. Like, for example, if K is equal to 0, no, to 1, remember it's at equilibrium. If K is equal to 1, delta G is also equal to 1. And then E of the cell is equal to 1 as well. It's at equilibrium. Right? If it's positive, if delta G is positive, if you remember, it's non-spontaneous. K is under 1, and then the E cell is negative. And then if delta G is negative, K is over 1, E cell is positive. But again, and then here you will have a spontaneous reaction, right? So I can ask you, so going back to this question that I asked you, like, hey, calculate the E cell for the following redox reaction. After that, find the delta G of the reaction. After that, I can ask you, like, is the reaction spontaneous or non-spontaneous, right? So I can ask you that very easy, and you should be able to tell me, no problem, right? So again, the equation that we use is delta G is equal to E standard, is equal to negative NFE standard, right? Now, realize that we're using E standard here. We're using E standard, meaning that we're using conditions at standard. No, we're using like measurements at standard conditions, right? Standard conditions when it comes to chemicals is 1 molar. 1 molar. But what if you have a different number, a different concentration, right? If we have a different concentration, we have to account for that. That comes one last equation that I want to discuss. No, I think we're going to talk about a few more equations, but this is called the Nernst reaction, the Nernst equation. What is that equation? Is the equation when you don't have concentration at standard. So it says that E, the real potential, is going to be the standard potential that you calculate from those reduction potential minus RT over NF times ln of Q. What is Q? If you remember, is our quotient, right? It's ln of Q over our quotient. So it means it's going to be your concentration of the products over the concentration of the reactants, right? So if you have A to B, right? Q will be equal to concentration of B over concentration of A. Does that make sense? So again, this is if the concentrations are different from 1 molar, which is standard, because if you look at this, if they are 1, it will be ln of 1, and ln of 1 is 0. So this whole part will not be, will be 0, and then E will be equal to E potential, right? So the Nernst equation accounts for when we don't have the concentration of 1, right? So I can ask you like, hey, oh, this is good, this is very good, because they're asking, predict whether the following reaction would proceed spontaneously. So basically they're asking, calculate delta G. Calculate delta G. So proceed spontaneously means calculate the delta G. And if delta G is negative, we're spontaneous. If it's positive, we're non-spontaneous. How do we calculate delta G? We calculate it from the potential, right? And then how do we calculate the potential? We calculate the potential by calculating first the standard potential, right? So we now know that these two are different because you have different concentrations. So you're going to calculate the standard potential of this reaction, then you're going to calculate the potential at these different concentrations, and then from there you're going to calculate delta G. That's a good question that kind of encompasses all of them. So make sure that you look at this and practice it. But again, you go back to the table, you realize that the cathode, the iron has a higher reduction potential than cobalt. So iron undergoes reduction, cobalt undergoes oxidation, and then after that, what's the standard of the cell? It's going to be E at the cathode minus E at the anode, meaning iron, E of iron minus E of cobalt. You have the standard potential very easily. And then after you have the standard potential, we're going to use the Nernst equation, this equation right here, right, to get the real potential, because that is the standard potential, but the real potential accounts for concentration. So it's going to be equal to E minus the voltage over N, right, times ln of Q, right? So this is another way to write down the NF equation, right? So here is RT over NF ln of Q, but if you have RT already, right, at these degrees, right, you can actually simplify that even further by doing R, we have it, temperature is at this, standard 25 degrees Celsius over N times the Faraday constant that we already know. So the Nernst equation can be resumed to this, but if you are confused, just use the full equation, right? Use the full equation, right? Which is again E is equal to E potential, right? E potential minus RT over NF ln of Q. So this is the Nernst equation. We absolutely need to remember the Nernst equation, right? So again, this is a more simplified version of it, but you can still use the real one, right? And then it's going to be ln of Q, and the ln of Q in this case will be cobalt over iron, right? Because why? Because the full reaction, right? If you set up we set up the full reaction, which is this, right? So if you remember, in the equilibrium constant, we don't use solids, we only use liquids. So it's going to be the concentration of cobalt over concentration of iron. So it's going to be concentration of this over concentration of this. So that's what we use for Q. So again, you got the voltage, and remember, we are not, we are done, I guess, because remember, delta G, you can calculate delta G. Delta G is equal to negative NF E, right? So if you find E, you can add N, right, which is two electrons in this case, times F times E. But guess what? If E is negative, delta G, because you have a negative sign here, delta G will always be positive, And if it's positive, it's not spontaneous. So you don't even have to calculate delta G. The sign itself will reveal how spontaneous it is. So remember this table right here. If E is negative, delta G is positive, and we are non-spontaneous. If E is positive, delta G is negative, we are spontaneous. So the sign alone can help you, and if not, then you can set it up. You know, if you're confused, you can set it up or look at the formula or calculate delta G and see if it's spontaneous or not. Okay, so that is actually the Nernst equation. So this is some practice. So calculate the non-standard cell potential at 25 degrees for the following reaction. So I gave you Fe and its concentration, chromate at this concentration, Fe, chromate and concentration. So find the non-standard reduction potential and also tell me if it's spontaneous or not. Okay, all right, so that's your question 4. Okay, all right, so there's something else in electrochemistry that's actually pretty interesting. We call it a concentration cell, right? So a concentration cell is when you actually set up a reaction where you have the same chemical on either side, but it's just different concentrations. Right? And oxidation will happen when where you have low concentration. Reduction will happen when you have high concentration. And guess what? We end up having a movement of electrons, even though it's the same chemical, just at different concentrations. I like this, but it's very it happens all that. You can do that, and you will measure the voltage, and you will see the voltage. So from here, you can actually calculate the potential of that, right? The potential of that, and starting with the standard potential, because the standard potential is 0 for this one, right? Because it's 1 minus the same one. So the standard potential is 0 minus this, you know, taking into account the concentration. So this is the Nernst reaction, taking into account the concentration. So you can find the voltage of a concentration cell. So I can actually, let me see, boom. Okay, let's do a quick question of so question 5. Question 5 is calculate the potential E. Okay. For a concentration cell with 0.05 molar of zinc chloride and 2 molar of it's the same thing. The chloride and the sulfate won't be involved, guys. It's just the zinc ions, right? Calculate E standard E delta G the K EQ and then spontaneity, meaning is it spontaneous or not. All right, that's question 5, right? So let's look at what happens in batteries. Again, everything that we've been looking at happens in batteries, but they are kind of built weird. For example, a dry cell is going to have an anode. So zinc batteries have an anode. They have a cathode that is a bit more complicated, but still the same standard. But then it's dry, so it basically uses dry electrodes, right? So you have a zinc electrode outside, then you have a moist, a kind of a paste for the other electrode, and then you have a paper spacer in between. That's literally it. And then so basically a battery is a fancy compact version of these types of cells that we've been looking at, right? So a battery is a fancy type of these, right? So it's a fancy compact type of these that have electrodes, anode, cathode, bridge, and a way to measure the voltage or a way to harness it, right? You have a mercury, those little mercury batteries that you put in watches and stuff like that. For some of you, right? Same thing, right? It has zinc and mercury on either side, right? A car battery, for example, right? Same thing, right? It uses lead, and battery acid is in there as well to provide sulfuric acid. So H2SO4 is the battery acid, and is the acid in the battery acid. So your car battery is most likely going to use lead. But again, anode, cathode, solutions, movement of electrons, same idea, right? So lithium ion battery, this is most likely it's different. This is a less sophisticated part of what's happening in your phone, because lithium ion batteries are newer as well. So same idea. You have fuel cell batteries as well. So again, all of the batteries are basically everything that we've been talking about, a few more chemicals, a few more complicated, to allow for a movement of more electrons or faster, or storage conditions and things like that, but it's still the same idea. Corrosion is another electrochemical process. Why is it an electrochemical process? Is because if you do corrosion, for example, iron is oxidized, right? So iron goes from, so if you remember from corrosion reaction, iron plus oxygen becomes iron oxide, right? So iron oxide is like Fe. It can be Fe2, Fe2O3 or something like that. So it goes from iron. Can actually do this, right? FeO, right? So it can start by iron 2 plus, and then that iron 2 plus can turn into iron 3 plus. So corrosion is also an electrochemical process. Why? Because we are losing electrons, and then oxygen is the one gaining electrons, right? So we are losing and gaining electrons. That is an electrochemical process. And the last thing that I want to talk about is called electrolysis. Now, I love electrolysis because electrolysis is like the opposite of what we were just talking about, right? So a galvanic cell is how we use a chemical reaction to produce electricity, and electrolysis is the opposite. Electrolysis is how we use electricity to drive a chemical reaction that otherwise wouldn't have happened, right? So electrolysis right, is the process in which electrical energy is used to cause a non-spontaneous chemical reaction to occur. So this is the chemical reaction that otherwise wouldn't have happened, and then we make it happen, right? So look at this. If we have like chlorine and NaCl here, right, usually this is not a spontaneous reaction. It's not likely to occur. But here, look at this. We add a battery, we add power. And then when we add power, it's going to cause it to occur, right? So this happens a lot. This happens a lot where we use electricity to drive the production. So one of the most famous electrolytic reaction is electrolysis of water. Electrolysis of water. So this is breaking down water to produce hydrogen and oxygen. If you take water and then you add a little bit of acid to give it the H plus ions, right? And then you add a battery to it, it's going to produce hydrogen on one end. So this is, actually sometimes we do this in the lab, right? So we're going to produce hydrogen on one end, oxygen on another. So this is electrolysis of water. You break down water to produce H2 and oxygen gas, and then you do that by adding energy to it, because usually you can't just be like, oh, H2O becomes H2 plus O2. Yes, it does, but it's very hard to do that. If it was easy, we will be producing hydrogen and oxygen from water, but we can't. It's a it's very likely not to occur. The opposite is more likely to occur. So for us to drive this, we have to add a lot of energy, right? But you can do that. And by the way, it's like, this is how they do it. For example, in submarines, they can generate oxygen from water. And guess what? Like a hydrogen car, for example, there are some hydrogen cars that use electrolysis to produce hydrogen, and then they can use that to drive that car. So when you hear that there are cars that are powered by water, this is what they mean. But of course, the reason why these cars haven't replaced the normal cars is because yes, you can drive a car by water, by breaking down water to give hydrogen and use hydrogen as fuel. But guess what? You need energy to do that. So where will that energy come from, right? So but still, we have hydrogen cars that are driven by water walking around. Most of them are actually not driven by water. The water is used to produce hydrogen elsewhere, and then you can add hydrogen into the hydrogen fuel car, right? I really like that. But again, hydrolysis, very important, very cool process, right? You can practice, kind of look at this, but again, this is what's happening at the anode. H2O is becoming O2 plus H plus, right? At the cathode, H2O plus 2 electrons is becoming H2 plus O minus. These are the half reactions of what's happening when we break down water, all right? So this is question 6. Question 6 is, write the half cell reaction and the net cell reaction of the electrolysis of Na2SO4. What gases are produced at the cathode and anode? So if you've been paying attention, that's pretty much what we were just talking about. All right, so you can make some calculations from electrolysis based on how much, right? This is important. Based on how much current that you're putting into hydrolysis, you can measure how much of the chemical you should be producing, right? So you take the current, right? The current and the time that you're putting in, and then when you take the current is in amperes times time in seconds, it gives you the charge, right? So you go from current and time, which you can measure, right? We can measure this, you know, you can measure how much current you're adding and how long, and then when you multiply that, you should give you the charge, and then the charge divided by the Faraday constant, which is this is the Faraday constant, will give you the number of moles of electrons, right? And then if you look at the number of moles of electrons, you can use the mole ratio in your half-cell reaction to get the number of moles of what was produced, right? The number of moles should give you the grams. If you remember, we use molar mass, right? You can use molar mass to go from moles to grams, right? So let's look at an example. If I ask you like, a current of this much is passed through an electrolytic cell containing a dilute sulfuric acid solution for 7.44 hours. So write the half cell reactions and then calculate the volume of gases. Okay, the volume of gases actually this is actually another thing, right? If you remember, 1 mole of gas, this goes back to your gas laws. 1 mole of gas at STP, or standard temperature and pressure, contains 22.4 liters, occupies 22.4 liters. So this is what you get. You're going to get the moles, and then from the moles you're going to calculate the volume like this. So don't be confused when they ask you something like that. But if they give you sulfuric acid, they are basically talking about that the H2O, right? They're talking about the H2O plus O2 reaction, right? So this is it. We already looked at this earlier, right? This is the electrolysis of water, right? And then this is, from here they're asking you, so write down the half cell, right? And then calculate the volume. It's very easy to calculate the volume, because what we do, we're going to calculate, so the amperes times the seconds will give you the charge, right? The amperes times the seconds will give you the charge in coulombs, and then from the charge we're going to divide by the Faraday constant to get the moles, and then from the moles of electrons you get the moles of oxygen based on how, like, okay, they're asking for the moles of oxygen, so how do we find the moles of oxygen? You're going to be like, oh, okay, if you have, when you have, this is what they mean by ratio, right? When you have 4 electrons produced, you have 1 mole of oxygen. So when you have 4 moles of electrons produced, you have 1 mole of oxygen, right? So whatever number of electrons produced here, we're going to divide it by 4, okay? So that's the ratio. So let's see, okay? So again, you're going to calculate the amperes into seconds, right? So they gave us hours, so you multiply by seconds. The amperes into seconds is going to be your voltage in coulombs, right? Then from the voltage, divide by the Faraday constant to get the moles of electrons. The moles of electrons. But again, they ask for the moles of oxygen. So as I was just talking about it, 1 mole of oxygen is produced by 4 moles of electrons. So we divide by 4 to get the moles of oxygen, right? The moles of oxygen. And then from the moles of oxygen, if you have the moles of oxygen, you can do, you know, from what we know about this, we can calculate the grams, you can calculate the volume, right? You can calculate anything, really. How do we calculate the grams? If you remember, I use this equation, but you can also do your you can just do dimensional analysis, but moles, right? N is equal to mass over molecular weight, right? So to find the grams, you take the moles times the molecular weight. You get the grams. What the molecular weight of oxygen is 32. Is it 32? 32 grams, yes. All right, you can get the mass here. How do you get the volume? Again, as I said, 1 mole occupies 22.4 liters, right, at HTP. So don't even worry about these. Don't even convert these will give you the same thing. So just take the number of moles times 22.4 liters, right? And if you do it, you should get the same as this, right? Because that's how it's calculated. So again, you should be able to calculate these very easily, right? So now let's see. This is question 7. Question 7 says a nickel strip is used to plate chromium, right? And chromium solution, we're using electrolysis, right? So chromium, we're using chromium and we're using electrolysis, and then they're asking you how long in seconds must, I like this, I really like this, must a 1.5 ampere current be applied to deposit 0.2 grams of chromium. Okay, so here's something really cool that happens, right? So when you, let's go back to the galvanic cell and I'll show you. All right, so this is a galvanic cell where you have zinc. Here you have copper sulfate. It produces electricity. You can add a voltage here, or you can add a light bulb and it's gonna work, right? This is a galvanic cell, right? So an electrolytic cell or doing electrolysis is the opposite. If you add a current here, right? If you add a current here in a method that was not likely to happen, you can use that to deposit metal. You can use that to deposit metal. So this is called electroporation, right? So here you have a cell, here you have another cell, then you can even use plastic, by the way. It's actually really cool. You can do this, right? You can add, instead of adding a meter, you add a battery right now. You add a battery and then you connect them, right? And then you start, right? If you start, you can coat this, right? Because you're driving the deposition of metals, right? Like for example, gold, right? You can deposit. So if you have gold particles in solution, you can drive the current and the gold particles will deposit on whatever you have. And guess what? This is how you coat fake chains with gold, with like a layer of gold, right? They're not fake, but yes, this is how you coat things with gold, right? With electrophoresis. So it's called electroplating, right? And trying to see if I can show you like a picture of the process. It's actually pretty cool. So the picture here is kind of what's going on, right? This is the setup, right? You can plate like a silver spoon with gold by putting into a gold solution. Have gold, you run a current through, and before you know it, your silver spoon has been plated by gold. And what's happening in the solution shows you is on this side, right, where you have a gold anode, you have a gold solution, right, and then you run a battery, and then that will drive the gold to be plated like that. It's really cool, but it is still electrophoresis, right? So that is what this question is referring to, right? You are doing it with chromium, but then if you remember, we go from current times time is equal to voltage, right? Voltage, and then we know that voltage voltage over the Faraday constant is equal to moles of electrons, right? And then when we take these moles of electrons, you just do an arrow. Moles of electrons will give you the moles of what we want. Here it will be chromium, right? And then the moles of chromium will give you the grams of chromium, right? So we just did it on oxygen, so you can do it on chromium, but guess what? This question is doing it the other way. So it's, and remember here you use the molar weight, right? Here you can use the ratio, if you remember. So you have everything you need, but here they gave you, let's set up the things that they gave you. I'm just trying to help you so that you're not stuck on this one, right? So they're asking for time, so let me put it in red. They're asking for time, and then they gave you the current, right? So if you have the current and they're asking for time, that means you need to find the voltage. We don't have the voltage, but guess what? They gave us the grams, right? So if you have the grams, you can go from grams to moles. You can go from moles of chromium to moles of electrons. And then from moles of electrons, you multiply it by the Faraday constant, you get the voltage. And then when you get the voltage, you can find the time, right? So that's, I just solved it for you. But this is kind of giving you a hint so that I can help you solve it, because it's not a straightforward path like the example that we looked at. Sometimes we'll look at the example and then it's when I ask you, it's gonna be like the opposite or the twist. So I want to kind of show you how to think about it if the question that they have asked you is not straightforward. But that is electrochemistry in a nutshell, and you should now understand in general how electricity is produced using chemical reactions, how we store electricity in batteries and things like that. You should know about electrolysis. You should know how to calculate the voltage. You should know how to calculate delta G and what it means, spontaneous, non-spontaneous, unspontaneous, and things like that. So you should know all of that. And I think that is enough for today. This is an important chapter in chemistry, and hopefully we've taken time to explain it fully. But if you have any questions, feel free to reach out, and I'll see you in the next chapter. Bye-bye.